Okay, welcome to another operations research video. So this one is talking about integer, binary, and mixed linear programs. This first video is going to be tips and tricks, essentially helping you think through how can we use integer and especially binary variables mixed in with our continuous variables in a linear program. And we've seen some examples of linear programs where some or all of the variables needed to be integer variables. For example, the post office scheduling, if we needed to schedule a certain number of workers, we can't have partial workers. And so integer variables usually come up when you're not allowed to have fractional values. On the other hand, binary variables is what we're going to focus on in this video. And binary variables are really powerful because they allow you to essentially encode a bunch of logic into your model that wouldn't be possible otherwise. Okay. And kind of just a heads up for notational purposes, I'll let X be continuous variables, and I'll let anything with a Y be a binary variable. Okay. So the basic application or how you use a binary variable is as an indicator, essentially an answer to a yes or no question. For example, should we build a new factory in Fargo? Value of 1 indicates a yes, value of 0 indicates a no. And so it allows you to have those sort of yes or no type questions built into your model. And if you think of decision making, not all decisions are how much, but rather should I or should I not. And so binary variables allow you to encode a lot of that logic aspect of decision making. So there are a lot of interesting ways you can use these binary variables within a linear program. So we're still keeping our constraints linear, but they sort of encode a lot of that logic. So I'll kind of run through a bag of tricks, and then we'll have several example videos that sort of talk through and show these tips and tricks in an example. Okay. So first example is if you've got mutually exclusive options. You can essentially sum up each of those binary variables and say that they're less than or equal to 1. This guarantees that no more than one of the choices can be positive or yes. For example, if you want to consider 3 different sites for that new factory, you can create a binary variable for each of the potential sites, but you only want to build a single factory, and so you'd want that the sum of those binary variables has to be less than or equal to 1. Or maybe you want to allow up to 2 factories, right? You can say less than or equal to 2. But essentially, when you got binary variables and you add them up, you're saying how many yeses do I have? Okay. And so this limits the number of yeses that you can have, in this case, to at most 1. Okay. Contingent decisions, sometimes one decision depends on another, and that in this case, if you constrain y2 to be less than or equal to y1, then y2 can't be 1 unless y1 is already 1. Okay, if y1 is 0, it forces y2 down to 0, or sort of conversely, if y2 is 1, it forces y1 up to being 1. Okay. You can't have y2 equal 1 and y1 equals 0. So it kind of eliminates that possibility from there. And this can be really useful, for example, if you're trying to decide whether you should build a factory, but also need to decide whether you want to invest in a rail line, and you might not want to build the factory unless you also decide to invest in the rail line. And so the factory decision is contingent upon building a rail line there. And so you'd kind of have y2 as being the less than value on the less than side of things, and y1 being on the greater than side of things. And that would sort of force y2 to be 0 if y1 was already 0. Okay. And so I like to think of these as sort of turning on and off other decisions. And so essentially y1 can turn off y2, and y2 can turn on y1. So if y1 is 0, it forces y2 to also be turned off. If y2 is 1, then it forces y1 to also be turned on. And so they sort of push each other up or down and turn each other on and off. Okay, this is especially useful when you pair continuous variables with binary variables. Slight change in how it's set up is that you got your continuous variable less than or equal to some big M times 1 y1, where big M is an upper bound on the size of x1. And sort of if we move things to the same side of the equation, this is what they look like. With OMPR, you can keep your variables on both sides of the equation, and that's fine. And what this will do is essentially if y1 equals 0, then it turns off x1 and forces x1 to be 0. So you're not doing any of that activity. On the other hand, if x1 is bigger than 0, then it forces y1 to be 1. And so it sort of turns on that y1. And this is a really kind of common technique to use a pair of variables, one continuous and one binary, where the binary variable says, should I do any of this activity? Yes or no. And then once that's a yes, and y1 takes on a value of 1, then x1 controls how much of that activity should I do. Okay, and so an example of this is maybe y1 is a decision whether or not to build a factory, and x1 is how much to produce at that factory. Obviously, if you don't build the factory, you can't produce anything. And so if y1 equals 0, you need to force x1 to be 0. On the other hand, if x1 is positive, then you need y1 to be 1, and you have to build the factory in order to produce something. Okay? So contingent decisions is a pretty powerful trick, especially when you're pairing a binary and corresponding continuous variable together. Sometimes you have a choice of either or constraints. This might be the case when you have sort of two resources that you could use to get something done. And you're either using one resource and kind of your activities are consuming that resource maybe differently than the other resource. And so, yeah, you either need to satisfy this constraint or this constraint, but you don't need to satisfy both constraints because you're only going to use one or the other. And the way we can do that is essentially use a binary variable to turn off one of the constraints at a time. Okay, and the way we can turn off a less than or equal to constraint is that by adding a large positive value to the right-hand side. Okay, and so if y1 equals 1, this constraint, the second constraint, is turned off by adding a big number to the right-hand side. On the other hand, if y1 equals 0, then 1 minus y1 is 1, and then the first constraint is turned off. Okay? And so that big M essentially turns off the constraint by adding such a large number to the right-hand side that it's going to allow anything to happen on the left-hand side of the inequality. When you have less than or equal to constraints, and as long as you have non-negative numbers on the left side, then it's actually a little bit easier. Where if you're going to say either this or this, you just multiply by the y, or the 1 minus y. And that if y equals 0, then we're just saying that the left-hand side needs to be greater than or equal to 0. And so as long as your problem sort of already has that happening, this will take care of that. On the other hand, if you need to allow that your left-hand side could be negative, just do the same thing as up here and subtract big M times 1 minus y1 and subtract big M times y. That would do the same. This is maybe just a little bit more clean and neat when you know that your left-hand side is going to be non-negative. Okay, so this is either one or the other, and possibly both could be satisfied. This still allows that it's possible that both constraints are satisfied, but only one is enforced. Okay. On the other hand, we can kind of generalize this even farther. So this would be 1 out of 2 constraints must hold. We can say k out of n constraints must hold. And so if you've got n different constraints and you don't need all of them to be satisfied, but you only need maybe like 9 out of 10 constraints to be satisfied, Then what you do is you do the same trick. This time you create separate binary variables for each constraint. And so here I'm creating n y variables, and we're adding big M times that y variable to each of those constraints. And so any of the constraints where the y variable is equal to 1 are essentially turned off. And then if we want big K out of n to hold, then n minus K are turned off. And this is essentially saying that n minus K of the y variables are equal to 1. And so n minus K of these constraints get turned off, which leaves K of them left on. Okay. An application of this specific trick is in implementing chance constraints with simulated parameter values for the right-hand side. We might simulate 100 copies and only enforce that 95 of them have to be satisfied. And so this gives you a way of sort of probabilistically having a bunch of constraints, but saying not all of the constraints need to be satisfied. And you might only require that 95 out of the 100 be satisfied. Okay, and this is especially useful if unlike a normal chance constraint where you maybe have a nice normal distribution and you know where the 95th percentile is or the 5th percentile is, sometimes you have a kind of more nebulous distribution of your parameters, and simulation is an easier way to deal with that. And so you might be bootstrapping samples from past data. So that's K out of n must hold. You can also use this to have some tricky kind of possibilities for functions that kind of show up in either a constraint or really the objective. And suppose you have discrete levels of a certain resource. So maybe there's some sort of discount or kind of package deals where you can kind of choose, or are you going to subscribe to the basic premium or pro level of some subscription for your company. And it might be that there are different levels or different numbers of sort of help calls or requests that you can run at each of those different levels. And so in this case, we sort of have a left-hand side, and then for the right-hand side, we've got binary variables y1 through y5 that essentially will turn on and off each of the potential values of that right-hand side of 1, 4, 9, 16, or 25. And then this constraint here enforces that exactly one of the y's will be true. And so only one of the values on the right-hand side will be picked up. And so four of the y's are going to be 0. One of the y's is going to be 1. And so if, for example, y3 is 1, then you're going to get 9 on the right-hand side, and all the rest of these are going to be zeroed out. So that's a nice trick where sort of things come in discrete steps, but not evenly spaced, maybe. Okay, and so that's a nice trick. One of maybe the most common tricks is dealing with startup costs. A lot of activities, when you're thinking about your objective function, have both a fixed cost and a variable cost associated with them. So the fixed cost might be having to do with kind of buying the machinery in order to start doing a process. And then the variable cost might be the cost of running the machine. Okay, and there may be some ways of kind of getting around the variable or the fixed cost. Sometimes you see in analysis, you sort of amortize the value of the machine over the life of the machine. And so you sort of kind of annualize the cost over 10 years for that machine and kind of build it into the operating cost. But sometimes you want to deal with that fixed cost separately. And so your objective might be to minimize the total cost. And each of these individual costs are going to have some fixed cost, that's the KI here, and then some per unit cost, that's the CI here, where it depends on the number of units of X. Okay. Whereas if X is 0, then the overall cost is 0. But notice if I plug in 0 to the formula up here, I'd still have the KI. And so essentially that KI needs to be turned off when X is equal to 0. To accomplish this, we kind of have that trick of a pair of a binary variable that goes along with the continuous variable. And so this is the constraint that we kind of introduced earlier for a contingent continuous variable contingent on a binary variable. And we're going to use that trick, and that's going to turn on and off the fixed cost. And so that K value is going to be multiplied by the YI. So when YI is 0, we're not charged any fixed cost. If YI is 1, then KI is 1, and YI is forced to be 1 whenever XI is positive. Okay. I will say it might seem like there's an issue in that when XI is greater than 0, then it forces YI to be equal to 1. That we want, right? However, you'll notice that if XI equals 0, then your Y is sort of free to be either 1 or 0. And this might seem like a problem, but the trick is that the minimization will actually push it to 0 so that it doesn't incur that fixed cost. This trick, though, only works when you have a positive fixed cost for minimization or a negative fixed cost for maximization. So yeah, it wouldn't really work to have that optimization push it off unless this is the case. Okay, a last tip or trick is what I kind of call sliding window constraints. If you got a whole bunch of binary variables and they maybe represent activities that are in a sequence. So are we going to schedule Greg to work first shift or second shift or third shift or on down through ninth shift? But we don't want to schedule the same person to have too many shifts in a row, right? And so you might want to prevent runs. And so in this case, we're going to say we're only going to allow up to 3 shifts in a row. And then if they work 3 in a row, then they need to not work a 4th in a row. Okay. And if we want to prevent runs of 4 or more, then what we do is we have constraints where we put 4 consecutive variables in there, and then constrain that to be less than or equal to 3. And so we can't have all 4 of these in a row be true. Okay. And then you need to slide that window of 4 consecutive activities down through the end. And so you'll notice that if you've got a lot of binary variables or long strings of them, you can potentially add a lot of constraints in order to implement these sliding window constraints. Of course, you can generalize this to either longer or shorter runs. You might want to have no consecutive shifts, and then it would be just two consecutive variables less than or equal to 1, right? So this number here is going to be the maximum length of your run, and then the number of variables you have over here is always going to be 1 more than the maximum length of your run. Okay. Lastly, a little bit about Boolean logic. This comes up some of the time. I'll say the first 2 come up the most, the last 2 maybe less often. But you can kind of think of each of these binary variables as a Boolean true false. Okay, and so we can use a couple of the tricks or operators from Boolean algebra, which if you've kind of dealt with computer science for a while, you might have seen before. Otherwise, not too much, and that's fine. I will say maybe the reason why I've included some of these is another application of binary variables is on logic puzzles, and in logic puzzles you might run into things that are more like some of the other ones on this list. But so first off, if you want to have one variable and another variable that essentially records the opposite of that variable, that's the not operator. It flips true to false and false to true. And that's a pretty simple, just take 1 minus the binary variable to get its not version. Okay, and we sort of saw that before when we used 1 minus y on the either or constraint. So 1 minus y always has the opposite value as y. Okay. And this is probably the most useful or more one. And if you are familiar with Boolean algebra, the way you often accomplish an and in Boolean algebra is multiplying. And so if you kind of think about, okay, 1 times 1 is 1. So this over here is the truth table of what the result should be. And so, and you need to have the output be true if both the inputs are true, but 0 otherwise. And so if you kind of think about this, you could think about this C, this column here, as being the multiplication of A and B. Okay, and that would give you exactly this column. But if you multiply two variables, it's no longer a linear program. And so there's this little trick where you can transform what would be a single nonlinear equality into a pair of linear equalities. And so C has to be less than or equal to the average of A and B and greater than or equal to A plus B minus 1. Okay, this second one pushes it up to be 1 here. This first one pushes it down to be 0 for all of these. Okay. Sometimes I'll say you only need one or the other of these because you only really need to push up or push down. And so you can kind of think about that in the context of the problem that you're dealing with. Though I will say, when in doubt, it's not usually worth the extra brain power to decide whether a constraint is needed or not. You can include it and then let the optimization decide whether it's needed or not. Okay. Or is true whenever either A or B or both are true. So this is what we'd call an inclusive or. And you can accomplish this with two inequalities that C is less than or equal to A plus B, and it's greater than or equal to 1/2 A plus B. And so that will accomplish this here. And then the last one is an exclusive or, which has a value of 1 if either A or B are true, but not if both are true. Okay, and so it's only true if A and B have different values. Okay, and this takes 4 inequalities to deal with. 2 of them are sort of push down, or less than or equal to's, and 2 of them are push ups. And so depending on your application, you might only need the push down side of things or the push up side of things, depending on what you're going to use C for. Okay, that's it for my bag of tips and tricks. We'll proceed with the next couple of videos showing you some examples.